Greetings and welcome to a new video about full-wave rectifier controlled by thyristors. In this example, we'll again look at the RL load where we see now the CCM and also in addition to that the BCM. So CCM stands for the continuous current mode and BCM is the boundary current mode. We will see what the differences are and also what the effect is on our circuit parameters. Of course, we'll see everything step by step in our calculations and verify these in MATLAB Simulink simulations. We have an input voltage again, 200 sine 100 pi t. So the frequency is 60 Hz and our amplitude of our source is 200 volts. The load will be a series RL, 100 ohm resistor and 500 millihenries of an inductor here. So that's actually shown here. Again, the same configuration as we have discussed in the previous full-wave controlled rectifier, where we see here again the 4 thyristors and the gating signals G1 up to G4. The delay angle is again the alpha of 55 degrees as we have it before. The only change with the previous example is that the L here is increased from 50 millihenries to 500 millihenries. So we will see what the effect is on the values here. So we again calculate the average load voltage, the average load current, etc. And we'll also compare the results in this example. Okay, let's go first to the calculations for this example. Again, I represent our input voltage using the omega t domain instead of the t, so that will be more handy. And again, here the Vm is our amplitude of our source voltage, 200 volts, and the omega is our radian frequency, 120 pi radians per second. Let's first discuss the conduction mode for this circuit. The conduction mode depends on our operating frequency, the values of our load, in this case resistor and the inductor, and the delay angle we have chosen here. So the load current is continuous if the delay angle is less than or equal to this theta, which is called the impedance angle or the load impedance angle, and that is given by this expression. So again here, the continuous mode will happen when the delay angle is alpha equal to or smaller than this load impedance angle theta, again given by this expression. It can be also discontinuous. We have discussed this in the previous example. Then the delay angle is larger than the load impedance angle. Again, the load impedance angle is given by this expression, as we also see it here. So that depends on the reactance of the inductor and also the value of the resistor here, and also, of course, our operating frequency. So in this case, we will substitute here the values for our inductor and the resistor, and the omega we have here. That will result in 1.083 radians, which is approximately 62.1 degrees. And we see indeed that this is larger, the theta now in this case larger than the alpha here, so that means actually the conduction mode here is then CCM. That's actually the first case. Now the plot will be different than the situation where you have this DCM or the discontinuous current mode. The input voltage will be still the same, that's the red line or red curve. Now the blue output voltage is then quite different than the situation where we have the DCM. So you see again it follows the output, but it is actually on the flip version for the part where the T3 and T4 are active. And when the T1 and T2 are active, so these two thyristors, it will follow exactly that shape, and then again it will flip its value you see actually here, and then becomes actually the same operation for each period. The period of our load voltage will be 2 times smaller than the period of the source voltage. Now the interesting part here is especially the load current. You see here that the pink curve here, which is our load current, is now above this zero line, which means that we have a continuous current mode, as we have also seen this in the converter designs like the buck converter and the boost converter. So for CCM, the load current is given by this expression, which is a little bit different than the load current expression for the discontinuous current mode. So we see again here the load impedance angle theta. We see here the Vm, which is our input voltage amplitude, the impedance Z, and also the alpha we choose here as our delay angle, and also see other parameters like the tau. So let me summarize them here. So the Z is given by this expression, the theta again, and the tau is our time constant given by this expression here. Now from the given information, we can calculate now this Z here, which is our impedance. Just substitute here the values. You get here 213.4 ohms. Our time constant is 0.5 Henries divided by 100 will be 5 milliseconds. And then you substitute here everything from the given, and these values we get here, this expression, just substitute here in this expression. Now making this a little bit more readable, just 200 over 213.4 will be just 0.937 approximately, and then also work out here the parentheses and the parameters here that will result in this expression. Okay, now let's move on and first calculate the average load voltage, which is actually this part. And that is given again in a similar form as we have done before for the DCM. That is given by this expression. You can now substitute here the VM, which is R200, the alpha, which is 55, so it is the exact same result, which is then 73.03 volts. The average load current is done using Ohm's law, so you actually take this value, divide by the resistors, that's actually shown here, and that will result in, again, exact same value as we have before with the DCM, so 730.3 milliamps. And now the change will be for the load voltage and load current. So the average values for the load voltage and load current will be exact same as for the DCM and the CCM, but for CCM we need to do this in a different way using Fourier analysis. So the voltage across a load can be expressed as the Fourier series, where we have the DC term and the harmonics, which are the AC terms, and those harmonics are only the even harmonics. So the expression is given by this formula. You see here the VO, which is our load voltage, is equal to the VO capital, which is our average load voltage or DC term, and the summation of a lot of AC terms, actually infinite, but only the even part. So n is 3, 2, 4, 6, 8, etc. But we need to actually get the values for this VO, n. Those are the amplitudes we are interested in. And here the omega 0 here is defined as the fundamental frequency, where we discussed here because that was 120 pi radians per second. Okay, now the DC term, as we have done it also before, that is officially again written like so, because the period is here in this case, you can also see that here, which is pi, because it's from starting at alpha up to pi plus alpha. So you see actually also that in the integration, and you also divide by pi. And when you do that, you get exact same result as we have done it before here in question A. So that will be used here. But the AC terms are given by this expression, where you see here the coefficients from the Fourier analysis, A sub n and the B sub n. So we need to determine these two parameters, so these two coefficients. So those are given by these two expressions. So this is quite complicated, and you see also the order here for the harmonics. So the n, the alpha is appearing, and in this case we have for the A sub n the cosine expressions, and for the B we see the sine expressions. We also need the amplitude Vm from our source voltage. Now we need literally actually go one by one, so we substitute here n is 2, n is 4, n is 6, also do that for B, and then use this formula to calculate the associated AC terms for this situation. So again, this is only valid for the harmonics for even n is 2, 4, 6, etc. Now the load current harmonics can be then determined using superposition and taking each frequency component separately and combining them together. And then we will use the Ohm's law. Like so, we have now the harmonics for the current, which are the harmonics for the voltage divided by the impedance. And that impedance will change, of course, because we have now n is 2, n is 4, etc. That will definitely change this value. It's not just a fixed value anymore. Okay. Let's now go to the RMS load voltage here. That is actually in this case pretty simple, because if you do the integration here, you see here the VO squared, which is our load voltage squared, the same expression we use for the RMS values. We know the VO, which is our load voltage, is exact same as our input voltage for the part from alpha up to pi plus alpha. So we can also say we use the expression for the Vs, which is actually shown here. So we replace this by Vs. And when you do the integration here, you will get Vm over square root of 2, which is a simple formula we know from the pure sine wave expressions. Now when you substitute here the value here, that means actually the VO RMS is also the V source RMS. That means 200 over square root of 2 will be then 141.4 volts here. So in this case, you don't have to go all the way through this Fourier analysis, not specifically for the RMS load voltage, but for the RMS load current, we need to go to the harmonics values and then calculate the components one by one. You can also do the VO RMS, so the load voltage RMS, by taking actually that in this format where you see the load voltage average value and also the harmonics in the RMS values each squared and add them up together. So this is also possible, but this is much faster and also the same result. Okay, let's bring them together and then summarize here what we need to do. In this case, the best way to represent the data is using a table. You see here the harmonics n from 0 to 4 up to 16. So we need to go actually in even orders. And you see also the frequency and the coefficients an and bn here. Now from here we can calculate now the VON, which are the AC terms, and then calculate from there the RMS values and the Zn, which is actually this formula, and from there the current amplitudes using Ohm's law, and then from there just divide by square root of 2, you get here the RMS values. The first row here is just DC, so that means the frequency is 0, that means the impedance is just 100 ohms, just pure resistive. That is also the average load voltage, which is from question A. Exact same RMS value, because the DC value and RMS value for the first the DC value are the exact same. Also the load voltage is the exact same, and also the load current, and also the value of the RMS value of the load current is also the same. So this part is as we have it before. Now we go to the second harmonic, which is then NS2, which is then 2 times the 60 Hertz. That means 120 Hertz. And that will go in here. And then we'll also multiply it by 0.5 and do the math here, and you get here the impedance of 390 ohms. Now this one A and B, so the A2 and B2, that can be calculated using these two formulas. When you substitute here NS2, the alpha, and our VM of 200 volts. And when you do that, you get here minus 114.0, and the other one is minus 93.31. Then you take these two values and substitute in this formula. You square it here, square there, add them up, and then take the square root. And that will result in 147.3 volts here for the second harmonic. Now how do we go from here to there? You now do the square root of that one, square root of 2. So you divide by the square root of 2, I must say. So this 147.3 divided by the square root of 2. So you actually consider each of these as a pure sine wave, and you go from the amplitude to the RMS value. And then you can take this and you divide by then the 390 to get that. And you also take this one again and you divide by the square root of 2 to get the component of the load current RMS for this second harmonics. In a similar form, you go for the fourth harmonic, so 4 times 60, which will be then 240 Hertz. Similar form, you substitute here the value, and also there you get the A and the B. Do the calculation again here for the AC terms and do the same procedure. You see here E minus 0.01 means actually this is then this value times 10 to the power minus 2, and also similarly here in these values here. Okay, now let's bring these values here together and then continue with our next calculation, which is our RMS load current. Now for that we need to use this last column here and then use this formula to calculate the RMS load current. So we need to take the square root of the sum of the squares of each terms here. So you see here the average load current, the second harmonics of the load current, RMS, etc. So those are all here. You see that 2, 4, 6, etc. Actually infinite. In this case we take actually a finite part of it, this part, and that will result in 779.9 milliamps. Now we can also do that. That's actually question C. We already did this, but you can also take this column here, which is then this column, and also take in a similar form the square root of this part, and that will result in 141.4 volts. Not maybe up to this point, but if you take long enough, so sufficient parameters, sufficient terms, that you get also close to this value we already have calculated. Now, question E, which is our observed load power, that can then be calculated using the RMS load current squared times a resistor in this case, and that will then here 0.7799 squared times 100, that will result in 60.82 watts. The final one is the power factor, which is defined as the load power over the apparent power, and apparent power is given by the source voltage RMS times the source current RMS. Source current RMS is equal to the load current RMS because we have here a series connection. So the source current is always the load current in the RMS values. And also the source voltage RMS is just the amplitude divided by the square root of 2. That is the simple formula we know, and that will result in this 141.4. Now taking this together in this formula, multiply that, you get here 110.3 volt amperes. That will be then here substituted using also the value from question E. And you get here now a power factor of 0.55 approximately. Okay. Now let's now go to the simulation data, and first we start with the pulse generator settings for the delay angle. You see here the Simulink circuit and a lot of details, so let me go one by one. This is the pulse generator for activating the gates of T1 and T2. Those are actually these two, which is actually shown here also, the G1 and G2. And the settings for that will be then presented shortly, and this is for T3 and T4, which is then activating these two thyristors. So I will bring up now the settings for T1 and T2. That's for the pulse generators. You see here the calculation for that. We know the alpha, you divide it by the 360 degrees and also by the frequency of this situation, which is 60 Hertz. And that is the time here of 2.546 milliseconds, which is also what you need to do here. So this phase delay here, which is given in seconds, is then calculated using this formula. Now, similar form for the pulse generator for the thyristors T3 and T4. There you need to shift that by 180 degrees, so it's actually shown here. So the exact same formula, just 180 degrees added in the numerator, and that will result in 10.88 milliseconds, and that's also shown here. So that's actually what you need to do. Okay, let's now go to the Simulink circuit and then verify our calculations in this situation. You see here the average load voltage as we have calculated, 73.03. The RMS load voltage is also exactly as we have calculated, 141.4 volts. The average load current is also what we have calculated, and the RMS load current is also as we have calculated. So this is all verified. Okay. Next part is about the Simulink plot, so that we will also see the waveforms. First we start with the pulse generator signals. These are for the T1 and T2 thyristors, and the other one for the green is then T3 and T4. You see here the signal will come up at this time. It's approximately 2.55 milliseconds, and that is actually calculated also from this phase angle of the 55 degrees or delay angle, and that's indeed correct. So that's actually what we should do, and this will repeat each other again after 1 hour 60 seconds, which is our frequency, of course, 1 hour the 60 Hertz. And then the other one will go after the half of the period, so this will then start later. That's for the T3 and T4 for these two thyristors, and that can be calculated like so. And if you do the calculation here, you get here indeed 10.88 milliseconds, which is also what we see here. So this is how we do the gating for these four thyristors. Now, one of the important plots here, this is now the plot for the source voltage, source current, load voltage, and the load current. The red one, the yellow one, the green, and the pink color here. What you see here is what you recognize here. Let's start first with the load voltage and the load current. This first label is where you see here the value of alpha. It's actually this one. You can calculate that by taking this time here, which is then 0.002546 seconds, times r omega. So that's the way to convert the time in seconds into the radians. You see here 0.96 radians, which is actually also our delay angle. So that's indeed correct. The other one is, of course, pi radians later. So that's actually what you see here, this label and also that label. That can be calculated like so. So I can verify that it is indeed 4.10 approximately radians. That is actually what you see here. So if you take this time, multiply again by 120 pi radians per second, and that will result in this radians. You also see here the load current, which is then staying above that, which is then dictating that continuous current mode, as we also have sketched this here. So everything is correct and also expected as we have it, but the interesting thing about this yellow line, which is our source current, is having a little bit of different shape than the source voltage. It looks similar, but we have a kind of a jump here, which is actually because of this thyristor effects. Okay, what happens now is actually now the next part in this example, where we change our inductor value, because it was before here 500 millihenries. So we keep everything the same. We only want to see what the effect is of changing the inductor value. So the conduction mode, we have discussed that before, so let me summarize this here together here for the continuous and discontinuous. But in between you have the boundary, which we call the boundary conduction mode, and that means the delay angle is exactly equal to the load impedance angle, which is theta. This is the third condition actually. So for that we will have the boundary current mode, which is then BCM for short, and that can be then calculated using this formula for the delay, the load impedance angle. So it will be then set to alpha, that's actually shown here, and then we can go to the required minimum inductor current and a minimum inductor value. So in this case you see here the value for the alpha, which is again the arc tangent of this omega, and now you see here the L defined as L minimum divided by resistor here. So when you work it out here, so you can do the tangent of left and right hand side, so we get this value and then rewrite this, so you have an expression for the minimum required inductor value here. What you see here the alpha, the resistor, and our operating frequency in radians per second. And for this case, with 55 degrees and 100 ohm for the resistors and 120 pi radians per second as the radian frequency, this will result in a minimum inductor we need is 378.83 millihenries, so almost 379 millihenries. That is what you need minimum. If you go lower than that, that means you have actually the condition of the discontinuous current mode. If you go above of that, then you have continuous current mode, which is actually what we had, because we had here 500 millihenries in the previous discussion. Now let's go now here for this situation, and now for BCM, the load current expression is now much simpler. That's actually shown here. So you see the Vm again, divided by the impedance, and then times the sine omega t minus this load impedance angle theta. And this is only valid between the alpha and pi plus alpha. Okay, and then again here the impedance expression and the expression for the load impedance angle. Now it will change, of course, because now we get a new value for our inductor. So I will choose right at the edge the value for inductor in this case, and that will result in 174.3 ohms. If I also calculate the theta, new value will be then 0.96 radians, which is 55 degrees. This is of course not a surprise, because we already said that the theta must be alpha, so this is of course what we should get. Now for the average load voltage, the formula will stay the same, and also for the average load current, and also the RMS load voltage will be the exact same. The only change is the RMS load current here, which is going much faster than before. It is actually using this divided by the impedance, so sort of the Ohm's law, and then you have everything actually from A up to D. So let's calculate that again. These are the values we have here, and this is now the RMS load current, which is now here 811.2 milliamps. Now having that, we can calculate now the absorbed load power here using this new RMS load current. That will be then here 65.8 watts, a little bit larger than before. And now the power factor again, the same definition, absorbed load power divided by the apparent power again calculated using this formula. We need again the RMS source current and RMS source voltage. Now taking this together, and we have here the apparent power of 114.7 volt amperes. Again, a little bit larger because the current is also larger. And that will result here in a power factor of almost 0.57. So what do we gain actually by changing this condition from the continuous current mode to boundary current mode? So let's check that. So let's make a summary of the situation that we have discussed so far, the continuous and the boundary, but also the discussion we have seen in the previous video where we have the DCM. So I actually collect everything here. I think it's a nice summary, so you see in one picture what we have actually. This L was before in the previous video was 50 millihenries, and now the values are shown here for the average load voltage, load current, etc., up to the power factor. And now we have changed that by a factor of 10, the inductor value, which goes to 500 millihenries, and then you get actually these results. We have discussed this in great detail in this video. Now, we also said what happens if you look at the minimum required inductor value and then take that. That will be then BCM, which is then the boundary current mode. And that's actually this value. You see that with VO, the average values for the CCM and BCM will be exact same, and also for the average load current, and also for the RMS load current, load voltage, I must say. But the change will be in the RMS load current. Here, see, it goes a little bit higher, and also for the absorbed load power will be larger, and also the apparent power will be larger. What you do see is actually the following, which is interesting. The power factor here for the DCM is actually higher, which is approximately here 0.88. It will go drastically to 0.55, so a huge decrease, actually reduction, because of the CCM. Why? Because we have, of course, a very large inductor, so there will be a lot of reactive power. That's why we have this power factor, which is reducing. In this case, we have reduced the inductor, so we actually also reduce the reactive power there, so that will increase this slightly, not that much. That's also the reason where you see here the power factor, which is larger than the CCM condition. So this is actually a nice summary for these three conditions for this example. Okay, let's also look at the Simulink circuit results for this boundary current mode situation, where you again see the results here. And I will also again encircle the values here from this Simulink circuit. You see exactly as we have calculated. And also the source current RMS value of that one is exact same as the load current RMS. So that's actually also see here. In addition, we also see the plots for this boundary current mode. Interesting thing here is again our load, the source voltage, source current, those are actually in the same shape, only just shifted by this alpha or theta. So the delay is only by this theta, but the shape is exactly pure sine. There is no jumping here as we had seen before in the CCM. What we also see is that the load current here is now approaching this zero node here and then coming up again to positive, but it will actually stay always at zero or above zero, but it will never go below that. That is really the boundary current mode. And the load voltage has this shape as we had it also before for the CCM. Alright, it was our example considering the controlled full wave rectifier using the thyristors, and we have seen how the conduction mode can change if you change your inductor value from, in this case, 50 millihenries to 500 millihenries. For this example, we also looked at the critical value or the minimum inductor value to go to the boundary current mode. We also used our formulas and checked our results in the Simulink simulations. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.